Hi, welcome back to CS170, and this will be the last lecture for, I guess, this semester. Uh, I will be able to post up anything that you have in terms of questions and whatnot. In your recitation this week, there should be a review, but if there's things that you would like me to post videos on certain topics or whatnot, just make sure you send me an email and I'll do that. But in the meantime, uh, if there's no questions related to the final exam that I can cover, this will be the last lecture. So we're finishing up here talking about like the limits of computation. Okay. So the first part here is this idea of this universality principle. I don't know if there's really like from your standpoint, there's a practical consideration for this. It's just one of those things you just kind of know. And it'll be like probably another multiple choice question on the exam. And that's about it. But it's going to be in there. So we'll have to cover it. Okay. Um, so it's this idea about like all the different computers out there. I'm just going to say a couple, but there's a whole bunch of them, right? But let's say we're talking about Apple computer versus a PC. Okay. Um, what is the same about them and what's different about them? And so that's what this universality principle is talking about, right? Um, so this idea about is what makes one computer more powerful than the other, right? So on the one hand, um, one computer from a computation standpoint can do what another computer can do, right? And that's what pretty much the universality principle is talking about here. And so if you go down to the lowest level at the CPU level, um, you remember from earlier in the semester we talked about what the CPU does, right? Um, these are the basic instructions here, right? And it also refers to the chapter here, chapter 9, right? So is talking about these are the basic instructions that um, every CPU, every computer chip will be doing. Okay. So because of that, that means, you know, what one computer can do, another computer can do. But then why are they different? Well, they're different because the software that leverages these instructions can be different. I can choose to program one computer to be very focused on graphics, let's say, focused on personal computing, focused on the desktop, whatever. And then another computer could be more for, let's say, maybe uh, engineers or more focused on doing certain types of calculations, right? So even though the base foundation is the same, and all one computer can ultimately do what another computer can be doing, the layers of software on top of it that people choose to put on uh, can choose to emphasize certain aspects, right? Depends on what you're trying to use the computer for. Okay. And that's what this slide is talking about, right? So if all the computers are computing the same way, then really speed is a difference, and um, how it presents itself ultimately to the user, right? But the actual computation could be the same if you choose to do it that way. So for example, you can see like Apple computer, you can see there's emulators that you can put on top of the Apple computer to run PC software, right? And vice versa. You can do that too, right? So it shows that you can run like on any computer if you wanted to, right? It's just that if I program, let's say I program the Apple computer to be more focused on, I don't know, let's say the graphics and the desktop and whatnot, and then you wanted to simulate something else, then you're adding another layer of software on top of that. So therefore, you're taking more steps, right? And that's part of the reason why it would be slower. Okay. So speed would be the difference. The functionality would be the same. Okay. Um, that's really the main difference. So I don't want to spend too much more time on it because it's not really that big of a deal beyond this, right? It's just more one of those facts to know. Okay. Um, so make sure you understand these. There's going to be a question on this on the exam for sure. But in terms of your everyday work with computers, probably doesn't matter too much. Okay. And so this is also another, reinforcement of what I just said, right? Doing the same computation, but they're doing with different instructions. No, same instructions. I should say with different instructions. So like I said, with Apple Computer, they're more focused on one thing. So the OS and the software that's on top of it is geared one way. And then on the PC, it's geared another way. Okay. So yeah, you probably see things like this, right? Your computer, your phone gets these auto updates, right? And then you get to a certain point where, you know, you're back, at least back in the old days, even for now, for some places, like you don't even have enough you don't have enough space to do upgrade, right? Or they'll say, yeah, this operating system can't work on this computer, right? You see that with Apple, and you see that with PC. If you get you get an old enough piece of hardware running, like whatever latest version of Microsoft Windows that you're putting in. Okay, um, so uh, you know, basically you have the hardware, and then on the top of that is the software. Would be just not sufficient to run the latest stuff. And so the software vendor is not going to support these old machines, right? So one example would be, um, in the older machines, uh, because of like the technology at that point, maybe the number of bits it processed at a time was less than what it is now. So when the new software, that's programmed specifically to leverage the larger number of bits that it's processing, it's going to go to the old hardware and find out like the bus is not big enough to support what it's trying to do. So right away, it's not going to work, right? But there's other aspects where, let's say, the latest software is dependent on certain types of functions that are available that's part of the OS, the operating system. I keep on saying OS, that's operating system, right? And so if you have like an older operating system that has like a smaller set of functions, right? Then the new software that's going to try to look for the new functions, it's not going to find it. So again, it won't be compatible, right? Some of the functions could be stuff that you don't even see. It could be like some security stuff. It could be stuff that makes things easier to do, things that we didn't support as much before. You remember before, you can see there was like some operating systems and software that basically were text-based. They were basically just running like screens that show different text. Obviously, if you have newer stuff that's really very graphical based, or using touch interface, like someone is touching the screen or something like that. Well, if the old operating system didn't even have those type of things before, of course, it's not going to support it when you try to use it. So that's part of the thing about why you would have new software that may not work on the older computers. Okay. Okay. So this is more of a computer science topic. So this is trying to just maybe distill it and make it a little bit more basic from, let's say, a non-computer professional looking at it, right? So there's this idea of like computer algorithms, right? And they look at how efficient the algorithm is, right? So that's what this is talking about. So some common things would be like, sorting something, searching for something. What are the most efficient algorithms to do those type of things, right? So sorting and searching and whatnot, that's been like taught for many, many years. That's been something that's been studied. So there's like a lot of different approaches on how to optimize on that. So how do you measure a unit of work on that? So let's say you're trying to do a sort. They'll look at essentially the actual calculation itself. They'll look at how many comparisons it does to do the sort, okay? Or to find something, how many comparisons it has to do to find something. Excuse me. So that's kind of what it's talking about here. So, and then there's this idea of like, uh, let's say you have 10 items. To do your unit of work, do you have to do less than 10 units of work, let's say comparisons, or do you have to do 10 units of work, or do you have to do multiples of 10? So it goes up what they call like exponentially. It could go up squared, it could go up cubed or whatever. So those are like the general classes in terms of like how you look at work to do some of the more common types of algorithms. Okay. And so this talks about this, right? You know, K list and then size n, right? So basically you're taking the K items, multiply it by the n's, so you get the number of steps that it would take. I call them comparisons, but you can call them steps, right? And then, probably from a challenge standpoint, you get into like some of these like very big problems where like those numbers of comparisons that I talked about, or those units of work, it grows very quickly the more items you add to it. Okay, so this is like this is what they just call it, right? This is a particular type of problem, right? They call it the NP complete problems. So one problem is like the traveling salesman problem. And basically they're talking about like, let's say each of these little nodes here, like 1, 2, 3, 4, 5, 6, 7 here. Let's say those are like cities, right? But you can think about them as nodes in a network. It's kind of a similar type of thing. Airlines can look at it, same thing as the traveling salesman, right? It's like traveling between like cities, let's say, okay? You're shipping something, you're trying to optimize on the fuel that you're using. They all kind of fall in this type of traveling salesman problem, okay? So what does it mean? So it's talking about a salesman that has to travel to all the cities, in whatever path before returning home, okay? And then these lines that are in between, that's the distance, okay, between each of these cities, okay? So you want to minimize the sum of all these numbers, right? So for example, right, let's say I did like 1, 2, 3, like the number 1 through 7, right? So you do 12 plus 8 plus 11 plus another 11 here plus 6, 9, so on and so forth, right? Well, that's one path, right? But there's other paths that you could be taking also. And so you take all those different paths and then you add up those numbers, right? In some ways, it's kind of similar to when you're looking at like the other earlier problems with the chess and the, chess being one, but AlphaGo, Go would be another one. If you're trying to do a look ahead algorithm, as you add the number of steps that you're going to look ahead, the growth in the computation grows hugely, right? That's what I was saying was exponential growth, right, in the work. So similar type of situation here, right? And so these are examples of some pretty tough challenges for computers to handle right now. And probably, when quantum computing becomes more establish and mature, maybe that's some of the problems that something like quantum computing can handle. But for now, these are like the kind of the edges at what it can handle. Okay. Right. So this is what I was talking about, large data sets. Okay. And so along the lines of limits of computer science, continuing along that line, there are certain type of problems you can do it, but it would take a very long amount of time. And then there are certain things is what they call non-computable. Okay. So I kind of alluded to it a little bit. It gets very challenging when you talk about certain things like autonomous driving, right? And not all of it is really computational because of computational intensive, although that's a big part of it. Part of it is like there's some challenges, like even if you're not worried about the computation, where you have, like I said, some moral or ethical decisions to make. You can't even decide how to do that as a person, let alone have a computer try to figure out how to do it. Okay. But you have things like computer vision, right? Artificial intelligence, we kind of talked about. And then you have very complex systems, such as like determining the weather, right? So things like this is like another challenge, right? It's very computationally intensive. So factoring a very large number. So this is one notable point on this is that encryption is driven off of like trying to do this type of hard type of factoring. So, and then the last thing is the halting problem. Okay. This is similar. I mentioned this kind of earlier, talking about like whether there could be a computer program that can automatically debug your code, right? Notably in terms of finding out whether something is going to be infinite loop or not, right? So that's kind of similar to this halting problem, right? So you have a program and then you have some input, okay? And the input could be anything, right? It could be like well, it depends, right? It could be a string, could be a number, whatever, right? And then it will say, will it halt given an input y, right? Sometimes it may, and sometimes it won't. It will go into an infinite loop. So this is what I was saying, like in terms of debugging, like some of these for loops or just loops in general, given certain types of input, will it go into an infinite loop? So for a computer to be able to figure that out, that's sort of a challenging thing. That's kind of why you don't have computers being able to, they can do some basic types of debugging, find some basic syntax errors, obviously, because it couldn't even compile it itself. But if you let it try to find like things like an infinite loop, it would be a challenge for it to figure out. Okay. So anyway, this finishes up the lecture for computing challenges. Let me know if there's any questions. You should be able to refer to the book for any more examples of this. And, if, like I said, if there's anything related to the final exam that you're not getting enough information, either from the recitation review sessions or from office hours, let me know. From my own office hours, like I said, send me email and we'll just kind of schedule it at whatever time kind of works for you. I work during the day usually, so probably something more like around nighttime would be better. But just let me know if there's anything you'd like to review for the exam, and I'll make the time for it. Okay. So thank you, and good having you this semester, and good luck with your finals.